Welcome back. In the previous lectures, we have been seeing about continuous functions and the space of continuous functions and the dense subsets of the space of continuous functions. In this lecture, we are going to look at the compact subsets of the space of continuous functions. So to begin with, let's start with a definition of total boundedness. So if X is a topological space and if E is a subset of the topological space, then we say E is totally bounded if for every epsilon there is a finite collection of points x1, x2, xn of the capital X, the topological space, such that E is contained in the finite union of epsilon radius balls centered at xi. So whenever this happens, then you say E is totally bounded. As an exercise, try doing this, that if you have a totally bounded subset of a topological space, then the n times Cartesian product of E, which is a subset of the n times Cartesian product of X. So if E is totally bounded, then E power n is totally bounded in X power n. It's not a difficult proof. You can use the definition and extend it to the Cartesian product situation. Now we say a subset A of the space of continuous functions where X is a topological space. So we say any subset of Cx is bounded if there is a natural number such that the sup norm is less than or equal to m, right? Because Cx, if you remember, is given in the supremum norm. So we say that f is bounded if sup norm is less than, basically means mod f of x is less than or equal to m. Okay, and this happens for all f in A. So whenever this happens for every element of A, so you can find a uniform m for all f in A, then you say that A is bounded. Now let's see the definition of equicontinuity. We say a subset of the space of continuous functions is equicontinuous at a point x0, at a fixed point x0 of capital X, if for every epsilon you can find an open set around x0 such that f of x minus f of x0 is less than epsilon for all element in this open set U and for all element in the set A. So this is the notion of equicontinuity at a point x0, right? So basically it's the definition of continuity, right? For every epsilon there is an open set such that this is valid. The thing is, this epsilon that you this open set that you obtain for any given epsilon is valid for uniformly for all f in A. Okay, so whenever this happens, we say A is equicontinuous at x0. We say A is equicontinuous if it's equicontinuous at every point of capital X. Now let's prove a result about the fact that for a compact topological space, if you have a totally bounded subset of the space of continuous function, then that subset is also equicontinuous. That is, totally boundedness implies equicontinuity for compact topological space. So to prove this, take any subset of Cx and let's assume that it's totally bounded. So by definition of totally boundedness, for any given epsilon, there is a collection, there is a finite collection of points from Cx such that A is contained in the finite union of these points of balls centered at these points with radius epsilon over 3. Okay, this is by the definition of total boundedness. Now each fj, which is an element of Cx, means it's continuous. So each fj, and for each x next there is an open set. There is an open set ujx, open set containing x, right? Such that this fj is less than fjy minus fjx is less than epsilon by 3 for all y in the set. This is by the definition of continuity of fj. This is valid for each fj in this finite set, right? Now what you do, you take, now this is a finite collection of open sets, you take the intersection of these open sets, so you get an open set U which contains this X, and if you take any F in A, right, we need to show that A is equicontinuous, right? So we need to check that the definition of continuity is valid uniformly for any element of A, right? So for any F in A, you choose J such that F belongs to this epsilon by 3 radius ball centered at Fj. This is possible by this fact that A is contained in this union. So if I pick any F in A, then this F should belong to at least one of these balls, right? So you pick that J to which this F belongs to, the ball to which this F belongs to. Then what we have is that for all y in ux, right, because for each y here you have this element and ux is intersection of this, so for all y in ux, if you look at this quantity fx minus fy and you add and subtract fjx and fjy, then this by triangle inequality becomes these three terms, okay, and this will be less than epsilon because the first and third term is less than epsilon by 3 by the continuity of fj. Oh, sorry, not continuity, by the total boundedness of fj, right? So this is less than epsilon by 3, this is less than epsilon by 3 because of this condition that f is in epsilon by 3 ball centered at fj. So this distance is less than epsilon by 3, this distance is less than epsilon by 3. And the second quantity here is by the continuity of fj, right? Fj is continuous, so we already seen this is less than epsilon by 3 here. So together this is going to give you is less than epsilon. What we have shown is that A is equicontinuous, that is we chose an arbitrary f in A. We have shown that fx minus fy is less than epsilon for all y in ux. This is what we need to check for equicontinuity. Fine. So total boundedness implies equicontinuity. Now we'll we will give the necessary condition for compactness in the space of continuous functions. So if X is a compact topological space, and if you look at the space of all continuous functions on X, then if a subset of Cx is compact, then that set has to be closed and equicontinuous. Okay, so in the metric spaces courses, you must have, like in Euclidean spaces, you know this necessary and sufficient condition, this equivalent condition for compactness, right? Which is any compact set is closed and bounded. This generalizes to the metric spaces as in any compact set, any set is compact if and only if it's closed and totally bounded, right? And this is here, which is for metric spaces. Here we are generalizing it to uh, for the space of all continuous functions. Notice that this is also a metric space. So the same, that equivalence is valid, that it's closed and totally bounded. But here we are giving the totally bounded in a property which is described in terms of equicontinuity. So checking for equicontinuity is much easier than checking for total boundedness and so on. So this is one way. We are going to do the other implication also at the end of this lecture. So this both this necessary and sufficient condition for compact subsets of Cx is what is famously called the Ascoli-Arzela theorem. Okay, so this is one implication here, which is that a set is compact if it's closed and equicontinuous. So let's prove this. It's from the previous theorem. So if because Cx is a metric space and A is compact, then the way I already said, for any metric space a set is compact if it is closed and totally bounded, and we just checked in the previous theorem that totally boundedness implies equicontinuity. So this implies that any compact set has to be both closed and equicontinuous, right? This is the theorem that we have used. Total boundedness implies equicontinuity, right? That's what we have used here. So now we are interested in the kind of converse of this. So what is the condition under which a subset is compact, right? The sufficiency. This is the necessary condition. What is the sufficiency condition? So can be done by some restriction on the range of uh, the functions here. So here when we say Cx, here we basically mean the real valued functions, but you could have even complex value and so on, right? So you can have the range. So if you put some condition on the range of the functions on capital X, then you can have a sufficiency condition for compactness. That's what we are going to see in this lecture. So first we prove this result that if X is a compact topological space and if Y is a metric space which is totally bounded. So Y is a metric space which is totally bounded. If a subset A, so Cxy means it's a set of all continuous functions from X to Y. Okay, that's what Cxy means. So the space of all continuous functions from X to Y. So any subset of that space is equicontinuous, then it's totally bounded. So this is the converse of the theorem that we saw some time back. There we showed that totally boundedness is equivalent to totally boundedness implies equicontinuity. Here we are saying that if the range is a totally bounded metric space, then equicontinuity implies total boundedness. So let's prove that. So we start with this assumption that the subset that we start with is equicontinuous. So by the definition of equicontinuity, for any epsilon and for each x, there is an open set ux containing x such that fy minus fs is less than epsilon by 3 for all elements in the open set and for all elements from the subset A. Okay, this is with the definition of equicontinuity. And this you can do for every x in capital X, right? Because it's equicontinuity at every point of x. So now what you do now, since you can do this for every x in x, if you do this for all x in x, you get a ball ux, and this ux running over all x in capital X forms an open cover of this topological space X. But X is compact, so that open cover will admit a subcover. So since X is compact, there is a finite set of points xi in capital X such that X can be written as the finite union of these open sets, right, by compactness of capital X. sorry, this is going down. Okay, so anyway, this is partially visible. So define the now you define the subset EA in the Cartesian product of the range y power n. Okay, what is the subset that you EA define? You have the set A. A is a collection of functions, continuous functions from in CXY, right? So you take the A, you look at all f in A, and you have this finite number of points xi. You look at the value of f at all xi's, right? That will give you a tuple, n tuple, right? Because there are n points here. This you run over all f in A, right? That set, that is a subset in y power n, right? Because there's an n tuple here, right? So you take any f, look at its value at x1, x2 up to xn, write down that tuple, and do that for all f in A. Then you have a collection, you have a subset in yn, call that as EA. Okay, now because this is a subset in the yn, the metric that you give in yn is this metric, right? And that is what you restrict to EA as well. So what is the metric that you give here? Is just the usual, right? So you have Cartesian product, n times Cartesian product. So you take maximum of the coordinates, right? So distance between 2 points is the difference between the coordinates of each coordinate and maximum of these coordinates. Okay. So here y and z are elements of this y power n. Okay. Now we have assumed in the statement of the theorem that y d, which is a metric space, is totally bounded, and we have seen and I have given you an exercise already that if y is totally bounded, its Cartesian product is also totally bounded, which means y power n is totally bounded. So EA is a subset of y power n, so EA is also totally bounded. Okay, which means that by the definition of total boundedness, you can find a finite collection of points, right, which let's call at yj, and yj in y power n. Okay, yj such that you can such that e power a is in the finite union of balls centered at yj. Okay, so yj is an element of y power n. Okay, so and you have m such elements. This is by the definition of total boundedness of EA. Okay, and you see each yj is an element of EA because yj is defined as the union over fj's. Sorry, not union over, the tuple of fj's. Right, this is the n tuple corresponding to the image of fj, image of x1, x2, xn of fj. Okay, so and the existence of such an yj is from the total boundedness of e power a. Okay, so now if I take any f in the capital A, then there is a j such that the distance from zf is less than epsilon by 3. Okay, this is by the equicontinuity, right? So this equicontinuity is something that we have assumed here and we have assumed here. So for any f you have this relation, right? And that's what we are saying here. So sorry, this is in the not by equicontinuity. For any f, its image is in y power n, right? And in that metric of y power n, we have this relation because any f is in this ball of radius epsilon by 3. So this distance from this point is less than epsilon by 3. So this is from this this definition that EA is contained in this. Because if F is in A, this ZF is in EA, right? So if ZF is in EA, then there is a J such that it's in that epsilon by 3 ball, and that's precisely what we are saying here. Okay, so in particular what this means is that if you give any f, the way we argued here, for any f there is a J such that for all I this is valid, right? This is coming from this fact from here, right? Because Yj is this, Zf is this. So for and this metric is maximum of all these difference of these points, and maximum, and each of this is less than the maximum, and maximum itself is less than epsilon by 3. So each coordinate there is less than epsilon by 3 here. So this definition is what gives you this. This is maximum over all such, maximum over I basically, right? So here we are doing this for each I, right? So now for any f in A, if we choose our J such that whatever this happens, if we choose the J for which this happens, and for any x in capital X, there is an I such that x belongs to uxi, because uxi is in cover, right? Uxi form a cover. So any any little x in capital X will be in some uxi. So for any x there is an I such that x belongs to uxi. For any f in A there is a J such that this happens. So now you choose this I and J for any f in A, and for a fixed x you choose I and J such that these two happens. Then if you look at this quantity fx minus fjx, then if you add and subtract f of xi and fj of xi, then by triangle inequality you have this these three terms. Now this first term here and this third term here, right, both these are less than epsilon by 3 by the continuity of f here and by the continuity of fj here, right? Both are continuous functions, so they both are less than epsilon by 3, right? Like for instance, that's how we chose J, right? So this J was satisfying this, so this is this is for here. So J was chosen such that the second term here becomes epsilon by 3, right? And here this is by the continuity at the x variable, okay, continuity at x. So we have continuity of f at x, continuity of fj at x, okay. So together they are epsilon by 3. So together if you sum them, this is less than epsilon, and that's precisely what you need to prove. So this is true for every x, right? So what we have shown is that for any f in A, there is a J such that the sup norm is less than epsilon. That's what we want, right? Because that's what we mean here when we say it's totally bounded. We need to show that there is a finite collection where A can be put inside the finite union. And we have precisely done that for any f in A. There is a J such that, which means, and these J's were chosen by the total boundedness of EA. So this completes the proof. Okay, so this means that if the range is a totally bounded metric space, then total boundedness, equicontinuity implies total boundedness. Using this, now there is another simple result, is that if you have a compact topological space and the space of all continuous functions on the compact topological space, then any subset of the space of continuous functions is bounded. If it's bounded, then there is a compact set K in R. So when I say R here, we have assumed here that these are all real valued continuous functions. So in the range, so there is a compact subset in the range R such that f of x belongs to K for all f in A and all x in X. Okay, so if you when you say a set is bounded subset of the space of continuous functions, then which means that you can find a compact subset in the range such that for all x and for all f in A, fx belongs to that, fx is inside the compact set. Okay, so basically the range of, basically the union of the range of f for all f in A is inside the compact set. Okay, so the proof is actually quite simple, right? I mean here, so you choose any element G and A is bounded. So if A is bounded is the assumption that you started with. So if A is bounded, when we say bounded, you use the metric here, right, which is the uniform metric here. So when A is bounded in the uniform topology, then there is an M such that this happens, right? Both of these are continuous functions, and if G is in A and A is bounded, for all f in A, this happens. Okay, f minus G is bounded by some number n. Now since x is compact and f is A, which means it's a continuous function, that means, sorry, not f, G is a continuous function, G is also in A. So if x is compact, the continuous image of a compact set is compact, so Gx is also compact, right? And Gs is a compact subset in the real line R. So Gx is compact, that means there is a capital N such that Gx is contained in this interval minus n to n, right? That's what compactness means. So Gx is contained in that. So what this tells you is that, so this tells you that f is less than, because from here I can say that f is actually m plus the supremum of G, and m minus the supremum of G, and so on. So from here we can conclude that if f minus G is m, then the f of, since G of x is contained in minus nn, and f minus G is less than n, then f of x is contained in minus n m plus n for all f in A, because this happens for all f in A. Okay, and G is anyway fixed. So this means that f of x is also contained in a compact set, and that's what we need to show, that f of x is contained in compact set for all, so the range of f is contained in compact set for all f in A. And these choice do not depend on the choice k, this choice k does not depend on, right, does not depend on, is independent of the choice of the little x and little f. And that's what we have here. M is independent of the x and f here. It is only depending on the bound of the set A. Okay, so if we define K to be this set, we are done. That's what we have proved. Okay, now we are ready to prove the converse part of the Ascoli-Arzela theorem, which is the sufficiency condition for compact subsets of the space of continuous functions. So if X is a compact topological space, and if you have a subset A of Cx, which is closed, bounded, and equicontinuous, right? So basically, you know this is a metric space, so we know any closed and totally bounded is compact. So now here we are replacing the totally boundedness assumption by bounded and equicontinuity, right, for the space of all continuous functions. So if we have a closed, bounded, and equicontinuous subset of the space of continuous functions, then A is compact. And conversely, we have already seen that if A is compact, then it is closed and equicontinuous. So what is the proof? We have already developed the entire machinery for the proof. So A is assumed to be bounded. So by the previous lemma that we have shown, A is contained in Cxk, where K is some, because A is bounded, right? So it is contained in a compact subset, right? Range is contained in compact subset for all A, right? That's what we have shown here, right? The range for all elements of A, capital A here, the range is contained in a compact set, and that's what we are using here. That A is contained in Cx, K. That is, the range is contained in K, which is a subset of C of X for some compact subset K. That is what from the lemma, from the previous lemma. Now, by the theorem before that, we had shown that equicontinuity implies total boundedness whenever the range is totally bounded, and that's what we have a compact set here. The range is totally bounded. So by that theorem that we proved, A is equicontinuous with range totally bounded, which means that A is totally bounded. Right? Range is a totally bounded metric space. A is totally bounded. Okay, so what we have shown is that from this we have shown that the assumption that A is bounded and the assumption that A is equicontinuous actually gives you that A is totally bounded. A is already closed. So any closed totally bounded set has in any metric space has to be compact. So that means A is compact. And that's a proof of this is the characterization of the compact subsets of the space of all continuous functions. With this we are done for today. In the next lecture we are going to probably see the compact subsets of LP spaces, right, the P summable spaces and so on. See you then. Bye.